Welcome back. It's late.
Sure is.
The house is finally quiet. The Slack notifications have stopped pinging, or at least, you finally muted them.
Hopefully.
Yeah. And if you're listening to this, there's a very good chance you spent the last 10 or 12 hours staring at a glowing rectangle, wrestling with logic, syntax, and probably a merged conflict or two that made you question your life choices.
The glamour of the job, right? It's just you and the machine.
Exactly. Just you and the machine. Usually we tear apart history or some obscure corner of economics on these deep dives. But tonight, we are doing something a little different. We're turning the lens on you.
On the craft itself.
Right, on the craft of writing code. We've pulled together a stack of articles, technical papers, and one very specific and I think pretty profound confession from a veteran engineer that is probably going to hit a little too close to home for a lot of our listeners.
It definitely hit home for me when I read it.
I thought it might.
Yeah, we're looking at the state of software engineering, specifically through the lens of this massive explosion in large language models. But, and I really want to be clear about this up front, we aren't talking about stock prices here.
No.
And we aren't talking about which chatbot is currently winning the benchmarks on Twitter.
Right. We are talking about an existential crisis in the profession. The source material opens with this confession from a developer who has been in the trenches for over 20 years.
A real veteran.
Exactly. We're talking someone who built the Web 1.0, survived the dot-com bubble, migrated to mobile, managed cloud infrastructure. I mean, they know how the machine works.
Right. They know why a hash map gives you an O of 1 lookup. They know what's physically happening on the spinning disk or the SSD when a database indexes a column.
The ground level physics.
Yeah, that fundamental physics of software. They understand the exact cause and effect of every single line of code they write.
And then they drop this bomb in the article. They said that around 2023, the ground didn't just move under their feet, it completely vanished.
Right.
Despite 2 decades of absolute mastery, they suddenly felt, and this is their word, blind.
Blind is a heavy word for an expert to use.
It really is. But they're describing this specific moment where they watched a model generate working code or explain a complex bug or, I don't know, write a poem. And they realized, I don't fundamentally understand how this thing is doing that.
Because it's not deterministic in the way we're used to.
Right. It's not like a compiler where you can step through and trace the exact logic. To them, it felt like magic. And for an engineer, magic is a terrifying concept.
Because if you don't know how it works, you can't trust it.
Exactly. That's the hook for tonight, that feeling. It's not just imposter syndrome kicking in. The sources we're looking at describe this not as a tremor, but as a tectonic plate shift.
The entire continent of software engineering basically lurched sideways.
Yeah. And the argument here is that if you're still trying to navigate this new landscape using the old maps, the maps based purely on deterministic logic, you're going to get lost.
So that's our mission for this deep dive.
Unpack the shift.
Right. We need to explain why this technology is fundamentally different from the code we've been writing for 50 years. Because according to our research, if you don't understand the mechanism of this shift, not just how to call the API, but how the brain actually functions, you're flying blind in the biggest transition since the internet itself.
The stakes are incredibly high.
It's the difference between being a tool user and a tool master.
Ideally, yeah.
Yeah.
But before we get to the complex architectural stuff, we have to clear the air a bit. There is just so much noise out there.
Oh, absolutely.
You open social media and it's either AGI is coming next week to take your job and eat your children, or it's just a glorified autocomplete, don't worry about it.
Fog of marketing.
Yeah.
The sources are very firm on this point. We have to separate the marketing narrative from the actual math.
So let's kill the sci-fi version first.
Done. It doesn't exist.
Thank you.
There is no ghost in the machine. There is no mind in the silicon that has desires or wants a vacation or is secretly plotting to overthrow humanity. It literally doesn't want anything.
Okay, so if it's not a digital mind and we strip away all the Silicon Valley hype, what is it really?
It is statistical pattern recognition. Period.
Just statistics.
It is a very specific, very sophisticated set of statistical techniques that have just gotten spectacularly good at mimicking the patterns found in human data.
I want to drill into that a bit because pattern recognition sounds kind of simple. It sounds like something my graphing calculator used to do. But the source uses an analogy that I think clarifies the scale difference really well.
Hmm.
It compares machine learning to a child learning.
Right, so think about how a human learns. You show a toddler a photo of a cat,
Okay.
then another one, then a dog. Eventually, the child just figures it out. They can look at a totally new photo, one they have never seen before in their life, and say, that's a cat.
Because they've built a mental model. They
Yeah.
know whiskers, pointy ears, fluff.
Exactly. Now, on the surface, the machine appears to do the exact same thing. You feed it 10 million labeled photos. It adjusts its internal parameters until it can consistently distinguish them. So, to us, looking from the outside, it really looks like the machine knows what a cat is.
But the source makes a very sharp distinction here. It says the machine doesn't know anything in the way we humans use that word.
No, not at all. To you, your cat is a living being with a personality. To the machine, cat is a mathematical function.
It's just math.
It is mapping pixel values to a probability score. It's executing a function, f of x equals cat. It is not forming a concept in a mind. It's finding a statistical correlation between a grid of numbers, the pixels, and a text label.
So why does that distinction matter to the engineer listening to this right now? I mean, if it works, why isn't it works good enough?
Because if you think the machine knows something, you will naturally trust it like a human colleague. But if you understand that it's just calculating probabilities based on pixel distribution, you can anticipate where it's going to fail. You know it's math, not magic. And math has edge cases. Math has strict boundaries. If you treat it like a person, you are going to get burned when it inevitably acts like a calculator.
And that leads us directly into the biggest idea in this whole deep dive, the shift from rules to learning. This is the part that explains why that veteran engineer we talked about felt so completely lost. We're moving away from the deterministic model of software.
This is the core of the tectonic shift right here. Let's look at the old way, the rule-based system. For the last 40, 50 years, if you wanted a computer to do something, you had to explicitly tell it how.
Step by step.
You, the human, were the architect of the logic.
The classic if-then-else statement. I mean, this is how I learned to code. If X happens, do Y.
Precisely. And the source gives a great example of this breaking down, the 1998 spam filter.
Oh, man, I remember those days. You're a sysadmin, it's the late 90s, you want to stop spam, so you sit down with your coffee and you just start writing rules.
Right. You write, if the subject line contains the word Viagra, send a junk. Simple. Done.
And that works for about 10 minutes.
Exactly 10 minutes.
Eh.
Because the spammers figure it out immediately. If they change the spelling, they write V1AGRA.
Right, or they put the text in an image.
Sure.
Or they use a zero with space right in the middle of the word.
So what do? You go back into your code. You add a new rule for the number one. You add a rule for special characters. You add a rule for the phrase urgent business proposal.
And suddenly, your nice, clean code is just this massive hairball of conditional logic.
Yes, it's thousands of lines of if this, then that. It's incredibly brittle. It's a total nightmare to maintain. And most importantly, you are always one step behind the adversary.
This is what the source calls the complexity barrier. You simply cannot write enough rules to cover the messiness of the real world.
You can't.
You can't write an if statement for every single way a sentence might be sarcastic or every angle a cat might be sitting in a photo. The real world doesn't fit in an if statement.
So enter machine learning. This flips the paradigm entirely. In the old way, it was human writes rules, machine follows rules. In the new way, it is human provides data, machine discovers rules.
I want to use the server analogy from the research here because I think for the back-end engineers listening, this is really going to be the aha moment.
It's a perfect example. So imagine you are debugging a massive distributed web app, and it's running slow on Tuesdays.
Just Tuesdays.
Just Tuesdays.
The classic Heisenberg. It drives you crazy.
Right. Now, the old approach is you, the expert human, coming up with hypotheses.
Yeah.
You sit there in a war room with your team, and you brainstorm. Maybe it's the marketing email blast. Maybe it's a cron job backing up the database. Maybe the traffic routing is weird.
You're trying to find the rule yourself. You're basically playing Sherlock Holmes, trying to deduce the cause from the symptoms.
Yes. But in the machine learning approach, you don't guess. You take 6 months of data CPU usage, IOPS, database queries, active user counts, weather patterns in Virginia, literally everything, and you feed it into the system. And you just tell the system, find the correlation.
And what does it find?
It might come back and tell you, hey, response times spike by 400 milliseconds when the background ETL job overlaps with a specific API call type, but only when the memory pressure is above 80%.
Which, as it turns out, happens to occur on Tuesday mornings.
Exactly. The machine found a pattern, a hidden rule that you didn't even think to look for. You didn't write the logic to check the ETL job against memory pressure. The machine discovered that logic from the data.
That is a profound shift in the actual job description of an engineer. It's almost like we're moving from being the architects of the logic to being the curators of the data.
That's a beautiful way to put it. And it completely explains why that veteran engineer felt blind. Their entire expertise was built on writing the logic step by step. But the new value is in curating the data set and evaluating the weird, complex patterns the machine finds. You aren't the writer anymore, you are the editor.
Now, we've established that the machine is learning patterns, but I want to manage expectations here. Because when we say things like learning and discovering rules, people immediately imagine a general intelligence, like, oh, the machine actually understands the server architecture. But the source makes a very clear distinction between what we have right now and that sci-fi dream.
Right. This is the difference between narrow AI and AGI, artificial general intelligence, and this is exactly where the hype train usually derails.
So let's define those clearly, because these terms get thrown around so loosely in pitch decks and on LinkedIn.
Everything we have today, AlphaFold solving protein structures, ChatGPT writing essays, Waymo driving cars through San Francisco, all of that is narrow AI. They're specialists. Hyper specialists, really. A language model is incredible at predicting the next word in a sentence. But it cannot play a game of chess unless it has explicitly seen text about chess moves. An image classifier can spot a tumor in an X-ray with more accuracy than a human doctor, but it cannot write a sonnet about it.
But wait, someone might say ChatGPT can write code and poetry? That feels pretty general to me.
It feels general because it was trained on both code and poetry, but it cannot take the underlying abstract logic of poetry and apply it to, say, driving a car. It doesn't possess what we call transfer learning.
Transfer learning, that's a distinctly human trait.
Right. If you learn Spanish, it actually helps you learn Portuguese because you understand the underlying concept of Romance languages. If you learn to drive a little Honda Civic, you can figure out how to drive a Ford pickup truck in about 30 seconds. You are a general-purpose learner. You apply abstract logic from one domain to a completely different one.
And machines just can't do that.
Not yet. That is what AGI would be. And frankly, nobody actually knows if or when that is coming. The source explicitly mentions the prediction trap here.
Oh, the long, embarrassing history of failed AI predictions.
It's famous in the field. In the 1960s, researchers confidently said we'd have human-level AI in 20 years.
Yep.
In the 2010s, they said 2030. We are historically terrible at predicting this. But, and this is the crucial takeaway for the listener, you don't need AGI to change the world.
No.
Narrow AI, these super specialized, highly scaled pattern matchers, they are powerful enough on their own to transform how every single software system is built.
So we don't need a robot butler with a soul to revolutionize coding. We just need a really, really good pattern matcher.
Exactly. If you have a pattern matcher that can reliably predict the next 10 lines of your boilerplate code with 90% accuracy, the economics of software development change overnight. You do not need a conscious machine to disrupt an entire industry.
Which brings us to the actual technology that made this possible, because for a long time, AI was kind of disappointing.
It was.
I mean, we had chatbots back in 2015, and they were terrible. They couldn't remember what you said 2 sentences ago. And then something happened in 2017.
The attention is all you need paper from Google. This is the moment everything changed. This is the birth of the transformer architecture.
This is the part of the deep dive where we need to get a little technical. Before 2017, we had things like RNNs, recurrent neural networks. And the source uses a frosted glass analogy to explain how they worked, which I really like.
Yeah, it's a great visual. Imagine trying to read a book, but you can only see one single word at a time through a tiny hole in a piece of frosted glass. You read the first word. Then you move the glass, read the second word, then the third.
Right.
By the time you get to the end of a long, complex sentence, it's really hard to remember exactly what the context was at the beginning.
Because you lose the context by processing sequentially. You're just holding it in your short-term memory.
Right. RNNs process data exactly like a human reads text, left to right, step by step. And because of that bottleneck, they were incredibly slow to train, and they fundamentally struggled with long-range dependencies. They essentially forgot the beginning of the paragraph by the time they reached the end.
And then comes the transformer, What did it do differently?
The transformer completely changed the game because of a mechanism called self-attention, and more importantly, parallelization. It allows the model to look at the entire sentence all at once.
The source uses a very specific sentence to illustrate why this matters. The sentence is, "The bank was steep, so we decided to fish from the other side."
This is the classic cocktail party example in linguistics. If you were an old RNN reading that sentence sequentially, you hit the word bank. Now, bank is ambiguous.
Right. Is it a money bank? Is it a river bank? You don't know yet.
You have no idea, so you keep reading. I was steep, so we decided, and finally you hit the word fish.
And only then do you realize, oh, it's a riverbank. You have to mentally backtrack and update your understanding of the beginning of the sentence.
Right, but the transformer doesn't read left to right. It sees the whole thing simultaneously. It instantly connects the word bank to the word steep and the word fish. It resolves the ambiguity instantly because it has this mathematical mechanism to attend to relevant words regardless of how far apart they are in the sequence. It calculates the relationship of every word to every other word at the exact same time.
Though it sees the whole web of relationships at once. It captures the gestalt of the sentence instead of just a sequence of words.
Yes, and here is the massive engineering breakthrough. Because it doesn't have to go step by step, you can parallelize the training. You can spread it across thousands of GPUs running simultaneously.
So that's why we suddenly saw model sizes just explode.
Exactly. RNNs were hard to scale because you literally had to wait for step 1 to finish before you could compute step 2. Transformers are parallel. You can just throw more hardware at the problem. We went from models with millions of parameters to billions, and now trillions. And that massive scale is exactly what gave us the emergent behaviors we see in tools like GPT-4 and Claude today.
It's fascinating that it all really hinges on that one architectural shift parallel processing of context.
It unlocked everything.
But here's the rub. We have these amazing tools now, and a lot of developers are using them every day. But the source argues that many of them are doing it dangerously.
The black box problem. This is where we get back to the practical day-to-day engineering side of things.
Yeah. The question I hear all the time from devs is, why can't I just use the API? If OpenAI or Google gives me a clean endpoint, why do I need to understand how self-attention or the transformer works? I mean, I don't need to know how a combustion engine works to drive my car to the grocery store.
That is the most common argument out there. But the source counters it with a pretty brutal analogy. It compares using AI without understanding it to a web developer in 2005 using jQuery without understanding JavaScript or HTTP.
Oof, that hits close to home. I remember those days. You just copy-paste the snippet from a form, the menu slides down on your web page,
Right.
and you feel like an absolute wizard.
Okay, so it breaks. Until the menu doesn't slide down, or it conflicts with another script you pasted in, or it creates a massive security hole. And because you don't actually know the fundamentals, you don't understand the DOM, the request lifecycle, event bubbling, you are completely lost. You're just guessing.
So applied to AI in the modern era, what does that look like? What is the jQuery fail of 2026?
Let's look at the classic customer support chatbot scenario. The ignorant approach, the black box approach, is to just pick the biggest, most expensive model available, paste your company's FAQ documents into the system prompt, and hope for the best.
And the result is hallucinations. The bot starts making up return policies that sound incredibly plausible but are totally wrong.
And the engineer doesn't know why. They think, maybe I need a bigger model. Maybe I need to scream at it in the prompt. They start typing in all caps, do not lie, only tell the truth.
We've all been there. But the informed engineer, what do they do?
The informed engineer knows what the model actually is under the hood. They know it's just a next token predictor, not a factual knowledge base. They know it has a strict context window. So instead of just trusting the model to memorize facts, they use RO retrieval augmented generation.
Walk us through that briefly.
It means they write traditional code to fetch the relevant FAQ answer first, usually using vector search, and then they feed that specific verified text to the model with a strict instruction. Using only this text I just gave you, answer the user's question.
They constrain the probability space.
Exactly. They design around the mathematical limitations of the tool because they understand the tool. They know that the model is just trying to predict the most likely next word, so they rig the game. So the most likely next word is the correct factual answer.
That's the key distinction. It's not just about having the knowledge, it's about building an intuition. The source talks about developing an intuition for the downhill walk.
I loved this part. It was a bit abstract in the reading, but it's crucial. It's the mathematical reality of how these things actually learn. They are constantly trying to minimize error, what we call minimizing loss. You can visualize it as a ball rolling down a hill in a landscape with billions of dimensions.
Billions of dimensions. My brain hurts just trying to visualize 3.
Right. It's impossible for us to visualize perfectly, but the intuition you need is knowing that training is just gravity pulling that ball into a valley of low error. And sometimes the ball gets stuck in a local valley, a local minimum, where the model thinks it's right, but it's actually completely wrong in the broader context.
And that's why fine-tuning a model can sometimes make it perform worse.
Exactly. If you fine-tune it too much on a narrow set of bad data, you push the ball into the wrong valley. An engineer who treats it like a black box just says the AI is broken. But an engineer who understands the landscape says, oh, we overfit the model. We need to adjust the learning rate or check our data set quality.
It's the difference between a cook who follows a recipe and a chef who understands heat and acid. The chef can improvise, the chef can fix a sauce that's breaking on the stove. The cook is just blindly following instructions.
And in a world where the software landscape is shifting this incredibly fast, you cannot afford to just follow the recipe anymore. The recipe changes every single week. You need to understand the underlying chemistry.
So let's bring this home for the listener tonight. You have gone from that initial confession of feeling blind through the reality of statistical patterns, the shift from deterministic rules to machine learning, and the parallel processing revolution of transformers. What is the homework assignment here?
It means that if you are a software engineer today, deep understanding is no longer optional. It is a baseline survival skill. Now, you don't need to go build your own LLM from scratch in your garage. I mean, that requires millions of dollars in compute anyway.
Right. Please don't go buying 10,000 H100 GPUs. Your electric bill cannot handle it.
Please don't. But you absolutely need to know how to evaluate these models. You need to know when to use a small, fast model versus a massive one. You need to know how to debug them when they inevitably hallucinate. You need to move from being a consumer of magic to an engineer of probability.
I think that's a perfect summary. We are moving from logic architects to probability engineers.
That really is the new job title.
Before we let everyone go, the source left us with one final, slightly provocative thought. And it's about that moving goalpost of intelligence we touched on earlier. I found this really sticks with you.
It does. It's known as the AI effect. For decades, computer scientists said, okay, a machine will be truly intelligent when it can play chess.
That was the gold standard of human intellect.
Right. Then Deep Blue beat Kasparov in '97, and we all collectively said, well, that's just brute force calculation. That's not real intelligence.
Then we moved a goalpost and said, okay, the game of Go requires human intuition. A machine can't do that.
And then AlphaGo crushed Lee Sedol. And we said, well, that's just pattern optimization. Now we have machines that can write poetry, pass the bar exam, and debug complex C++ code. And we are still saying, yeah, but it's just next token prediction. It's not really thinking.
It really raises the question, are we actually defining intelligence, or are we just defining what humans do that machines can't do yet?
Exactly. Every single time the machine masters a task, we redefine intelligence to specifically exclude that task. It suggests that maybe our definition of intelligence is less about actual cognitive capability and more about human vanity. We just don't want to admit that what we do, our creativity, our supposedly unique logic, might just be incredibly sophisticated pattern recognition too.
That is a little unsettling to think about as we sign off.
Hmm?
Are we all just biological next token predictors running on a very efficient, wet neural net?
I will let the listener decide that one in the dark tonight.
On that existential note, we're going to wrap up this deep dive. Thanks for listening. Go read the papers, play with the models, and seriously, don't be afraid to look under the hood.
Good night, everyone.
Until next time.